All right, thanks very much. So today I'll talk about quantum learning of quantum data. Okay, so what do I mean by this? The idea is that you have some quantum data, like particles in a quantum state, and you want to learn something about them. So you're going to process them with a quantum computer, and then you're going to get a classical output, some kind of description or classical properties of the quantum data. And the goal in this problem is to get efficient learning algorithms whose efficiency is comparable to the analogous classical problems. Okay? I'd like to contrast this with another area of research, quantum learning of classical data. So here there's no atom signs around the dice. So the picture here is where you have classical data that you want to learn something about, but you're hoping to use a quantum computer to get exponential speedups in your algorithms. Okay, so that's the goal of quantum learning of classical data. And a key tool there is this HHL algorithm that was developed about 10 years ago. And we will not be talking about this in this talk. Okay, so no quantum learning of classical data, just quantum learning of quantum data. And another thing I want to mention is that I'm going to talk about what you might call unsupervised learning. So this is unlabeled data. The techniques or the problems we're going to be talking about are kind of akin to density estimation problems in classical learning. Okay, so just one brief slide about motivation. Actually, quantum learning of quantum data is something that takes place all the time, every day, in the sense that whenever you do any physical quantum experiment, like you try to build a little quantum circuit, or you do a quantum teleportation experiment between Tibet and the moon, like they did a few years ago, you need to check your work. You're trying to produce some quantum particles in a certain state or transfer some quantum particles. And you need to find out if you did it properly. So you need to learn the quantum state that is the output of your experiment. Okay, so people have to do this quantum learning of quantum data all the time. Okay, so let's go back to this picture. So as I mentioned, for this quantum learning of quantum data task, the goal is to have efficiency that's somewhat comparable to the analogous classical problems. Usually it's a little bit worse, but hopefully not too much worse. And so therefore, it may make sense for me to mention or talk a little bit about good old classical learning of classical data, where you have classical data you process with a classical computer to try to estimate some properties of the data. And as I mentioned before, we're going to be talking about density estimation kinds of problems. So let me even now remind you of a framework for classical density estimation. So this will be kind of a funny framework. I put it the way I put it so that I will most easily analogize to the quantum case. So here's the picture I would have in mind for the classical case. You have some probability distribution generating data, and I'm not going to make any assumptions about it, well, maybe except that it has a finite support. So there's an unknown probability distribution P, just with D outcomes named 1 through D. You can think of it as a D-sided die, where you do not know the probability of each face coming up. And you want to learn these probabilities or learn something about these probabilities. So you pay for m samples. You say, I'm going to do m samples to try to learn something about this distribution P. Okay, and then nature draws the samples for you, it draws from the m-fold product distribution, rolls the die m times, and you get some sample that looks like 2, 1, 3, 3, 1. Or rather, nature produces such a sample. And then the sample is revealed to the learning algorithm. It gets 2, 1, 3, 3, 1 as input. And then the algorithm thinks for a while about the sample, and then it outputs some kind of output x. Okay? And what is x? Well, it depends on what task you're trying to do. I mean, the most obvious thing you might try to do is just learn this probability distribution P to some accuracy. But you could be trying to do some other things, maybe try to estimate the entropy of P, or maybe you have some target distribution Q in mind, maybe the uniform distribution, and you're trying to test if, confirm or disconfirm the hypothesis that P is the uniform distribution. Okay, so there are many different things you might try to do with these samples. And you can see here also that here I'm mentioning the sample complexity of the learning algorithm, and here basically I'm mentioning the computational complexity. Both are important, but in this talk I'm mostly going to just focus on sample complexity. Okay, so this is some kind of picture of classical density estimation, and let me now tell you the quantum version of it. Okay, so it doesn't look too different, right, between the two slides, so hopefully that's good. So let me go through this slide and tell you about what quantum density estimation is. So again, you have some source of random data, and this is coming from particles in a quantum state. And these particles in a quantum state have some kind of dimension, d. And in particular, d is 2 to the n if you have n qubits. But let me forget about qubits, just so you have a d-dimensional state. And a d-dimensional quantum state has two components. you again have like a probability distribution, P1 through PD, but it's not just on outcomes 1 through D. It's a probability distribution on the vectors in an orthonormal basis of d-dimensional complex space. So this justifies my existence at Learning from Complex Structures workshop. So let me emphasize that from the point of view of the learner, P is unknown, and also the basis is unknown. Okay, so it's a fact that like the state of a d-dimensional quantum particle is a probability distribution over d orthonormal vectors. Okay, and this is what you're trying to learn, or at least learn something about. Okay, next bullet point, same thing. You say I'm going to pay for m samples. And again, nature draws, like m draws independently from this distribution. And therefore, like the realization of the sample is like m vectors from among this orthonormal basis, drawn from the product probability distribution. But like unlike in the classical case, like the algorithm does not just get to say, let me now see these vectors. Rather, the algorithm can only find out about the sample by applying a measurement. And I'll say what a measurement is later. But it's some kind of way of getting some probabilistic information about these vectors. Okay, so there are actually two probabilistic things happening here. First is the draw of the sample is probabilistic. And then the algorithm doesn't just get to see the sample. It gets some probabilistic information based on the measurement it chooses to perform. And measurements actually output classical data. So the algorithm might try to post-process this classical data. And then finally, it makes its output some estimate x. So that again, it could be an estimate of the probabilities p. It could be an estimate of the whole state, meaning the probabilities p and the vectors v. Maybe you just want to know the entropy of p. That's also meaningful quantumly, et cetera. Okay, and let me mention here that there's not just one kind of measurement. There are lots of different kinds of measurements the algorithm can do. And so therefore, the quantum learning algorithm is basically the measurement. Okay, like the smarts in designing the algorithm goes into like how to define a good measurement. Yeah? They can be even more than adaptive. So in fact, I'm going to talk about measurements just now. Thanks, Pablo. OK, so what is a measurement? I'm really going to get into like the math details. I know you're not too tired yet. It's only the second talk of the workshop. So like, hang in there. The first half has some stuff going on. OK, so what is a measurement? So first imagine that nature has drawn the samples. And let's simplify and just imagine m is 1. So there's just one sample. OK, there's this unknown basis. Nature draws a sample from it. So now like the realization is just like one vector v. Okay? And that's the thing that's going to get measured. Now, the algorithm's measurement is an orthonormal basis b1 through bd of the algorithm's choosing. Actually, technically, the algorithm can do something more sophisticated than this, but let me just leave it at this for the purposes of this talk. OK, so the measurements algorithm, which is actually corresponds to how the algorithm physically measures the particles, is specified by another basis. And then when you do that measurement to this vector v, what happens is you get back classical information, and you get back a number 1 through d, kind of corresponding to the d basis vectors b. And the probability that you get back j is equal to the squared length of the projection of v onto the jth basis vector. Okay, maybe you've seen this before if you've ever studied a little bit of quantum computation. OK, so since b is an orthonormal basis and v is a unit vector, these numbers are non-negative and sum up to 1. So this makes sense. And I'm just going to write it like this using properties of complex numbers. This is the inner product of b conjugate and then inner product of b and v. OK, so you kind of see how close, in some sense, v is to each of your basis vectors. OK. Now, the algorithm gets back this information, which is just a number between 1 and d. And then it's supposed to output its final answer, its estimate of something. And let's imagine it's only trying to estimate for now some kind of real number statistic, like maybe the entropy of the p's. So it gets back some outcome j. And let's say the algorithm is further defined by saying that when it gets back j, it outputs the real number lambda j. And that's the whole algorithm. First measure with b, get back 1 through j, and then output lambda j. Yep. Yeah, that's actually the algorithm's choice, b. So the algorithm doesn't know. It's kind of confusing because there's two orthonormal bases. But the algorithm doesn't know this sort of vector v that it's measuring, which was actually drawn by nature according to some distribution. But then the algorithm, like, of its own agency, gets to choose its favored basis. Doesn't know v, but it gets to choose its favorite basis, b1 through bd. And then this measurement happens. We know the basis. I mean, yeah. We don't observe b directly. Or, sorry, we don't observe v directly, but we infer information about it by doing this process. Yeah. Yeah, I'll get to that. So these probabilities are themselves random because we're going to come back to that. The v itself is chosen randomly. But first, let's imagine that like v has been chosen and like fixed. Yeah. So it is complicated because there's two aspects of randomness. OK, so let's look at the expectation of the output of this algorithm conditioned on v having been fixed. Well, it's just the sum overall measurement outcomes j of the probability of getting j, which is this, times the thing that you output on j, which is lambda j. And we stick the lambda j in the middle, and we stick the sum in the middle. And you see that the expectation of the output has a very compact form. It's v transpose AV, where A is this matrix. OK, and remember, this is all up to the algorithm's designing. It chose the orthonormal basis b, and it chooses these numbers lambda. And the measurement outcome, or the final algorithm, only depends on A through v transpose AV. And what is A? A is actually just any self-adjoint matrix, right? It's like any matrix with real eigenvalues. These are the eigenvectors. This is the eigenvalues. So basically, the whole algorithm can be described as, let me mention that in a second. The algorithm chooses its favorite self-adjoint matrix A. And when it measures this v, you can say that its output is a random variable with expectation v dagger AV. Okay. I also need to mention this for later. If you look about this, if you look at the expected square of the output, then it's just if I had lambda squared everywhere here. And it's the same thing with a squared, right? Because the square of this matrix is the same thing with the lambda squareds. Yeah. No, you can't choose it based on the sample. The sample is like unknown to you. So you get some particle in some state. You like pick your favorite matrix A, and you do this measurement process, and you output a real number based on that. OK. So as I said, you can just like forget for now like the b's and the alphas, and just say that an algorithm is identified with this matrix A, which is sometimes called an observable. And it's any old self-adjoint matrix. OK? And given a sample v, the algorithm's output is a random variable with this mean, v transpose AV. OK. Good. But back to quantum learning. As was mentioned, don't forget that the sample v itself is random. OK? Remember, it equals vi with probability pi. And another thing to not forget, which is making things more complicated, but it's still early, right, is that this is all if you have like one sample. You can actually pay for like m samples. OK, so just this is the picture, remember. You have this unknown probability distribution on vectors. Pay for m samples. Nature draws m samples. And you can apply whatever measurement you want to the samples to make your output estimate x. And it's even more complicated than that. This goes to Pablo's question, which is that you can measure the samples jointly. So one thing you can do is do this kind of measurement for each of your samples, collect like m real numbers, and do something with them. But you can also do like one big old measurement on the whole sample. So what do I mean by that? Well, actually, if you go back to this slide, I wrote it here without bringing it up carefully. But when nature draws, like in this 5 vectors, the sort of underlying state that you're measuring in that case is not just this list of vectors, but it's actually the tensor product of those 5 or m many vectors sitting in a really high dimensional space. OK, so perhaps the sample is this, if m is 5, is this vector, which is sitting in like the 5-fold tensor product of d-dimensional space. I told you it was going to get a little hairy. And the algorithm gets to measure this. So actually, the algorithm can specify any self-adjoint operator on this big space. And the algorithm's output is a random variable with mean, again, this vector transpose A times this vector. Okay? So it's looking a little crazy. Let's do an example. And we'll do an example with m equals 2, just the most non-trivial, no, the least non-trivial. Anyway, the next simplest case after m equals 1. Yeah.
Sorry.
Hey, Greg.
This like tensor thing that you cook up.
Yeah.
You have the same states repeated?
You may, yeah.
What does it mean that you have like 2 v3s?
It's fine. It's just like, for example, if d is 2, so the dimension is 2, you can think of like the vectors as like qubits, like the 0 qubit, that's here, and the 1 qubit. And this would be like, OK, if these 3s were, if the 2s and 3s were 0s, this would be like the qubit 0, 1, 2, 1, whatever, 0, 1, 0, 0, 1. OK, so it's.
Oh, I see. OK, these aren't actual qubits.
Yeah. So I mean, yeah. Maybe if I continue this example, it'll be a little bit more clear. This, we're at the most sophisticated part of the talk right now. OK. And this m equals 2 example will be related to something called purity estimation. OK, so we're the algorithm. And we get to choose an operator on this space. And we're going to choose a simple operator. It's the operator that swaps the 2 tensor components. OK? And I'd like to emphasize that this is a basis-independent operator. Like, it doesn't depend on the basis. So like this algorithm doesn't know the basis of v's, but you can nevertheless define the operator that swaps the 2 tensor components. OK? And its eigenvalues are plus or minus 1. So if you go back to this picture, like the algorithm's final output, it will be a real number, which is either minus 1 or plus 1. OK, and say, m is 2 here. Let's say, nature draws a sample, and it's, vj tensor vk. So the algorithm's output is some random variable. And here's the formula for its mean. It's, the vector, the big vector, dagger a times the vector. OK? And what does A do? It swaps the tensor components. So that equals Vj tensor Vk, dagger Vk tensor Vj. OK? And these are like unit vectors. These are unit vectors in the tensor space. And this inner product is either 0 or 1, depending on whether this whole thing equals this whole thing. And so you see it's 1 if j equals k, or 0 if j does not equal k. So now like a somewhat simple thing has happened. The effect of this algorithm, which outputs a real number, it's to generate a classical random variable whose mean is 1 when the 2 samples were the same, and 0 when they were not. And therefore, now let's remember that this sample itself was drawn probabilistically. Vj is drawn with probability pj. So what's the probability that in 2 draws you get the same outcome? Oh, it's like p1 squared plus p2 squared plus dot 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 pd squared. OK, so finally, if your algorithm involves taking 2 samples and doing this swapping operation, then your algorithm outputs a real number whose mean is this nice quantity, the sum of the squares of the pi's. And this actually has a nice meaning. It's like a quantity that one cares about. Actually, in both classical probability, this is the collision probability of the distribution. In quantum, it's called the purity of the state, and some property of the state you might care about. It's also basically the distance of, in classical probability, it's basically a distance of the probability distribution from the uniform distribution. Right? If you have the uniform distribution, this is 1 over d. And if you have, let's say, a distribution that puts all its mass on one outcome, which is very far from the uniform distribution, this is 1. So this is a number between 1 over d and 1. It's basically, if you subtract a little something, like the chi-square distance of p from the uniform distribution. OK, and it's, as I said, it's a quantity that you would care about also in quantum. And now you see this little 2-sample algorithm is like some algorithm that generates a real number whose mean is equal to this purity, which is something you might care about. OK, so now you can sort of forget quantum. And just think of this as a little statistics problem. A little exercise for you is that the second moment of this output is 1. That's really because, like, for the second moment, you need to look at a squared. And a squared is the operator that swaps and then swaps back. So actually, the mean of a squared is always 1. And In particular, that means you can't really say much more about this random variable's variance than it's at most 1, because this could be a very small number. So finally, you have some random variable whose mean is equal to the purity of the state, whose variance is 1, and you can use this to try to estimate the purity of the state. OK, so making a long story a little bit short and simplifying a little bit, you could repeat this whole sampling procedure, this algorithm d squared times, and estimate the purity to error like 0.01 over d, which is maybe what you need to do to get like a really good estimate, because the purity itself might be as small as 1 over d. OK. So this is a quantum algorithm for estimating the purity of an unknown quantum state.
Can we estimate the purity by using a one-sample algorithm? Like or will you show us some example where there's actually value in working with the tensor product rather than working with individual samples?
Yeah, I don't think you can estimate the purity. Aaron can correct me if I'm wrong, but I don't think there's any way you could estimate the purity if you only make measurements on like one sample.
Why not? I can estimate P by making this.
OK, you're right.
If you have lots of samples and
If
you
you-
measure each one
yeah.
separately,
Yes.
you can estimate the purity that way.
Yeah, right.
But it's, let's say that there's an order of D overhead to doing this.
Yeah.
So you can, the quality of this estimator does not depend on D, right? So you can, like if I want to know whether the purity is 1 or 1/2, the number of samples I need does not grow with D if I use this 2-sample estimator. But if you want to build it out of 1-sample estimators, then this is like the birthday problem, and it's going to grow like, or like at least root D.
Yeah. I should also mention that you can basically do the same thing with the classical problem of trying to estimate this quantity for a classical probability distribution. There, the variance is smaller, though, and so you can do this with ordered D samples. As I said, though, there's a better algorithm. And it's basically to not like waste your samples so much. And the same idea occurs in the classical version of this problem as well. So let me say what the better algorithm is. Let's say we pay for m samples, where m is big. Basically, what we can try to do is like do this like swapping algorithm on all the pairs and sort of average the results. Okay, and you can also do this in the classical case. And it's sort of like you're getting a quadratic gain. It's almost like you're taking m samples and like making m squared pairs. The thing is, they're not like independent of each other, so it's not like you freely gain this like quadratic factor. But if you work, you can analyze it. So let me say it explicitly. So let A be the operator that takes an n-fold tensor vector. And it's just the average of all possible swapping operators. So you look at all the transpositions of like, this is a symmetric group of order m. You look at all pairs of tensor components, consider the operator that swaps that pair, and you like average up all those matrices. Okay? And in general, I'm going to use this notation R of pi for the more general operator, which swaps around the tensor components according to a permutation pi. OK, it's not hard to see because each of these guys creates an output whose mean is the purity, that their average over all swaps still has a mean equal to the purity, which is great. And now hopefully the variance is a lot smaller, and we thereby get like a better estimate, as we always like. And you can do it. You can calculate the variance of this guy. It involves understanding the square of this operator, like analysis. And the upshot is that this is like a quadratically better algorithm. You can do this. I don't quite say what the problem is, but you can do it with order D samples. And this is tight. Actually, for some versions of the problem, this was solved even earlier by Aram. And I'll mention this paper shortly. OK, and if you know Paninsky's algorithm for estimating the distance of an unknown distribution to the uniform distribution, it's like highly analogous. And like Kostas has a paper that has an analysis similar to this. OK, let me look at this a squared now. because it gets into some interesting angles involved in quantum learning. OK, so what is a squared? Well, it's the square of an average. So it's the average of the operator that swaps according to overall transposition sigma and tau, of the operator that swaps components according to sigma, and the operator that swaps according to tau. And well, that's just the operator that swaps according to the, the product of the two transpositions, sigma tau. And in fact, let me just make the minor point here that this R is actually a group representation. It's an operator that maps a permutation for the symmetric group, permutation to a matrix that respects the permutation multiplication. And in fact, group representation is going to sort of get involved in a lot of this quantum learning stuff. So we can think about this, and this is part of the calculation when you sit down and work out at the variance and complete the analysis of everything. If you take two random transpositions and multiply them, what can happen? Well, you get the identity with some probability, cycle type 1, or they could be two disjoint transpositions, and you get cycle type 2, 2. Or if they overlap, which occurs with some probability, you would get a 3 cycle. OK, so this a squared is some linear combination of these three sort of permutation operators. And let me give a name to these. So let me define a sub t to be the operator on m-fold tensor vectors, which is the average of doing the tensor permutations pi over all pi's of a fixed cycle type t. OK, so then this is C1 times A cycle type 1, the identity. This is C2 times A times cycle type A cycle type 2, 2, and this is A3. And actually, the original algorithm A, which just averages over all transpositions, is this operator A sub 2. And here's a theorem. It wasn't exactly stated like this anywhere, but basically proved by Aram and Childs and Welch-John. And this version is in a later paper, which is this. If you're trying to estimate any statistic of just the probabilities that's symmetric, that only depends on the multiset, then the best estimator or the best quantum algorithm will be some linear combination of these operators. And the proof is because of representation theory. And it's really good. I loved to learn this theorem from this paper, because if you want, you can then sort of forget everything about quantum, and you're I don't really know what's going on. And it just becomes, because sort of what the optimal kinds of algorithms are. You don't have to search for the quantum algorithm anymore. You just have to analyze algorithms that have this nice property. OK, and the mean of any one of these ATs is some symmetric polynomial of the p's, and it makes things not too hard to analyze.
Can you make your is that a pointwise or uniform statement? When you say minimum variance, this is minimum variance, the minimum variance when I max over all possible statistics, or for each given statistic?
Oh, for each given statistic, among all the ones whose among all the A's, these outputs, whose mean is equal to that statistic of the p's, the one of minimal variance will be a linear combination of these special ATs.
Is it minimum variance or after constant factor?
No, literally minimum variance. And it's because there's a lot of symmetries in the problem that you can average over. You can average over the symmetries of reordering the samples, the M samples, because it's drawn from an IID distribution. And since you only care about the p's and not the v's themselves, you can also average over unitary rotations of the v's. And when you do all these averagings, you will always get an operator that's a linear combination of these ATs.
And just to be clear, this allows any permutation. It could be that the minimum variance unbiased estimator is the one that averages over all permutations.
Yeah, although this would probably be a trivial operator.
Well, maybe for a trivial statistic.
Yeah. OK. So let me just, quickly say that this is only about if you're trying to estimate a real statistic of just the p's and not the v's. But this is something you may often want to do, as it turns out. So we talked about how you might I mean, quantum people care about understanding the purity of an unknown state, how close it is to being a pure state, or very relatedly, how close these p's are to the uniform distribution, which is called the maximally mixed state in quantum. You might just care to know the maximum of all the p's, or the entropies of the p's. You know, for a quantum state, this is called the von Neumann entropy, but it has some meaning. And don't read this too carefully, but I just want to say that you can use this approach to get sample complexity results for all these problems, which are in many cases known to be tight. And you see they all have polynomial dependence on d and epsilon. And they're usually a little bit or somewhat bigger than the best sample complexity for the classical problem. In general, you can actually extend this representation theory approach to quantum learning problems where you're not just trying to learn a real valued statistic of the p's. For example, you might want to try to learn all the p's. So now your output is d numbers, not just one number. Or you might want to learn the whole state, which means the p's and the v's. You have to define that a little bit carefully. Or you might have a target state that you think this unknown state is supposed to be, and you want to try to measure how close the unknown state is to your target state. And again, there's some results showing algorithms that use this group representation approach to solve these problems. And in many cases, they're tight, and in some cases, they're proven by Aram.
So the lower ones are classical or what?
No, the lower bounds are quantum, but you can rely on the fact that's related to this theorem here. You can rely on the fact that you kind of know what the optimal algorithm is. So you kind of for any learning problem, you sort of know what at least for problems only involving the p's, you can kind of know what the optimal algorithm is. So it's a question of how well you can infer the property of the p's from the random variable outputs that you get from these special a's, which are basically symmetric functions of the p's. And therefore, it is sort of reduces to a quantum-free problem in analysis. And representation theory. OK. So in the last, 10 minutes or whatever, I want to say some final words about all of this related to practical efficiency. Because on one hand, I told you at the beginning of this talk that quantum learning of quantum data is in some sense not a far future fiction. People are always doing it all the time whenever you're running a practical quantum physics experiment. As I said, so say your goal in life is to try to build, prepare 8 qubits entangled according to a certain way. OK, you build your apparatus to do it, and then you have to check whether you succeeded or not. So you have to let's say, do this building process m times and do some learning on the results to see how close it was to what you intended. Similarly, if you're doing a quantum teleportation experiment, or if you're trying to build a small-scale quantum computer, you physically build your gates, but then you have to see are they operating correctly. So you have to learn what your gates actually do, or learn what no gate does, which is sort of learning how noise is affecting your quantum bits. And actually, this is even more interesting. This is learning a quantum channel or learning a transformation on quantum states, sort of the classical analog of learning an unknown Markov chain. OK, so on one hand, I'm trying to convince you that people are always wanting to do quantum learning of quantum data. But on the other hand, nobody ever uses any of the algorithms that I've talked about so far. So why not? Well, there's several good reasons. But let me mention a couple. OK, so first of all, these algorithms use entangled measurements or joint measurements. That is to say, we don't just take each sample and do a measurement on it individually. We take all m samples and do one giant measurement on all the samples. OK, and once you've designed your big operator A that operates on all samples, actually physically implementing it is probably going to be just as complex as building a full-scale quantum computer. OK, which of course we cannot do right now. So these m sample measurement algorithms are highly impractical, at least with today's technology. So all the algorithms I mentioned before, like maybe the quantum learning algorithms we'll be using like 30 years from now, but today we don't want to do them. It's sort of fair to say that like it's only feasible to build like one sample measurement algorithms A, and so like one interesting line of research is to understand what are the optimal algorithms in this scenario. For the problem of learning the whole unknown state, it's sort of understood. So Quang, Rahut, and Terstigi showed that actually with D cube samples that are of this like separately measure all the V's type, you can learn the whole state. And Ha et al., including Aram, showed that this is a lower bound also. So it's worse, but not too much worse. Actually, I think this lower bound might, the upper bound and maybe also the lower bound involve the model where like you specify in advance all M measurements you're going to do those measurements separately, get back some classical data, and then make your estimate. A slightly more sophisticated thing you can do, which is still, I think, technologically somewhat feasible, is like measure the first sample, get back some classical information, then choose your second measurement based on what you've seen so far. Do that, get back some classical information. So it's sort of like an adaptive one sample measurement process. So I'm not exactly sure what the scenario is for this slightly more sophisticated kind of algorithm. It's open? OK, so good. It's like, this is a nice problem. Actually, I know some like postdocs here at MIT that told me they were working on it, so I'm not sure if they're somewhere in the audience. OK. In fact, even this algorithm is not used in practice, though, because like the one measurement you have to do even for like one sample is like very computationally challenging to do. So I think in practice, people do a one sample measurement kind of algorithm with like a very simple measurement thing, and it requires like d to the fourth samples.
So what do you mean by from a quantum standpoint or from a
From a quantum standpoint, so this gets back to like a little lie I told, which is that let's say you have just like one sample and you want to do a measurement on it. I sort of said you get to like choose your favorite orthonormal basis, B1 through BD, and then you get back like one of the 1 through D with probability proportional to the square of the projection of the vector. You can actually do something like more general than that, kind of like choose like an overcomplete basis. And sometimes you need to do that. And implementing these is like more complicated. And in fact, the mathematician's way of like doing this algorithm involves like choosing like an overcomplete basis with like infinitely many like basis vectors. So that's hard. More than 10 or something, this is like very bad. And of course, we're trying to like build like quantum computers and stuff with like way more than 10 qubits. So this poly D is maybe arguably kind of a cheat. Although it's tricky because if your goal is to, let's say, learn the quantum state, which is defined by d real numbers and like d vectors, like what are you going to do? Like, I mean, you have exponential amount of size object that you're trying to learn. So unless you like change the problem, there's no hope of making progress. So one interesting way around this, which I want to tell you about in the last 5 minutes, involves an idea called shadow tomography, so named by Steve Flamia, introduced by Aronson in 2016, or according to like actually one of another paper, maybe introduced by Jaynes in 1957. So what is this problem? I should mention, for some reason, the quantum people call quantum learning quantum tomography. So like tomography just means learning in this context, but this is like shadow learning. So what does that mean? Basically, it means you don't try to learn the whole state because it's like an exponential size object, but you kind of try to learn some like operational aspect of this state, namely some things about like what would happen if you measured this state in different ways. It's a little hard to define, but let me do my best here. So let's say you have some state, which is a bunch of probabilities, a probability distribution over a bunch of vectors, and sometimes just encapsulate that all by the letter rho. And let's say it's applied to an observable A. This is like some algorithm that you might do, which produces a real random number when you do this observable A to this state P, rho. And its mean is this number. The average over all ways that the vector could be realized of V transpose AV. And let me just write this as the expectation of matrix A under state rho. So here's the shadow tomography situation. Let's say, as usual, we have sample access to this unknown state, but we have some like fixed observables or observations or hypothetical algorithms, A1 through AT, that we really care about. And we would like to know, like, if you were to run any of these AIs, what would be the expected value of AI under this distribution rho. And the goal is to learn all these expectations simultaneously to close accuracy. OK, so let's try to understand, without learning the whole state, try to learn some properties of the state, these t numbers. So the classical analog, by the way, is this problem, which turns out to be a quite trivial problem. You're given sample access to an unknown probability distribution of 1 through d. And you're also given like t fixed functions that are literally in your hands, the description that map outcome 1 through d to a real number between 0 and 1. And you want to learn all the means of these functions with respect to probability distribution p up to plus or minus epsilon. So just to check if you're still with me, can anybody tell me the classical sample complexity for this problem?
It depends on the FJs.
OK, on upper bound, if you don't know anything about the FJs. That's a good point, though, and perhaps a relevant point for this general problem. Sorry? Yeah, log t over epsilon squared, because if you're just estimating 1 for accuracy plus or minus epsilon, you'd need like 1 over epsilon squared samples. And you'd fail with probability, OK, if you do it log t times, then you'll fail with probability like proportional to 1 over t. So then you can union bound over all the t functions.
So you want to control the max accuracy here.
Yes, you want to control the max accuracy. OK, that's great. It's logarithmic in t, and it doesn't even depend on d at all. But let's go back to the quantum problem. The quantum problem, or the challenge of the quantum problem, is in some sense you cannot reuse the samples. So in the classical algorithm, you took a bunch of samples, used it to estimate f1's mean, and also simultaneously f2's mean up to ft's mean. But you somehow cannot really do this in the quantum case, unless the a's commute. So here are two things you might try to do. One, you could just be like, well, I'll draw a bunch of samples to estimate A1's mean, a bunch of samples to estimate A2's mean, et cetera. You can do each of these with 1 over epsilon squared samples, but you're doing it 2 times separately, so you get t over epsilon squared samples. Another thing you can do is just, I will learn the whole probability distribution, or sorry, the whole quantum state rho. This should say d squared, actually. And then once you learn using these learning algorithms, once you learn rho, you know everything there is to know about the a's. You can just write down all these numbers. This requires d squared over epsilon squared. So you see, we have either polynomial in t or polynomial in d here. But what Aronson showed a few years ago is that there's another algorithm that has polylog dependence on both t and d. OK, and that's great, because it inherits the polylog dependence on t that we want. And this thing is like the number of qubits. So it's hypothetically more feasible. In fact, that's not the last word on it. So this was his original paper. And then there was some follow-up papers. You might not notice the difference between these two things. It's like epsilon to the 4th rather than epsilon to the 5th, which is not so amazing. But what's interesting about these papers is they use a connection to online learning, which is very nice, and matrix multiplicative weights. And there's another paper, Aronson and Rothblum, that gets some different sample complexity. And the amazing thing about this is it uses a connection to differential privacy. So that's pretty cool, right? I mean, doing this shadow tomography by using ideas from differential privacy. OK, so I'm basically almost done. Let me just end with these open questions related to shadow tomography. So these are what we had before. Sometimes we see a log squared dependence on t, a poly dependence on epsilon, and some polylog dependence on d. One of my favorite open questions here is, can you get linear in log t times polylog d over epsilon? This is what I'd really like to do. And believe me, I tried the representation theory approach, and it didn't go so great. So maybe we need a different approach. Scott Aronson's favorite version of this question is asking whether you need a dependence on d at all, which we didn't in the classical case. Well, you don't if you just do this serial thing that uses t over epsilon squared samples. But the question is, can you get polylog t over poly epsilon many samples, an algorithm using this many samples? And in fact, as far as I know, there's no reason that you couldn't just have like a log t over epsilon squared sample algorithm like in the classical case. OK, I'll end there. Thanks. Yeah, Philippe?
So one more bullet point, which would be to be nice to have something that tells you how it depends on the FJs themselves rather than having this like worst case.
Definitely, yeah, and that's very, I don't know, that could be like the key aspect to the question. For example, if all these A's, which are matrices, commute, then it reduces to the classical case. So it does definitely depend somehow on the relationship between the A's, which is like understanding in the classical case, maybe you can do something better if there's a relationship between the F's.